This video is about our work specializing versatile skill libraries using local mixture of experts. This is a work conducted in the Autonomous Learning Robots group at KIT. Consider human motor skills. They are versatile, which means humans can execute different skills to a given task. For example, in table tennis, humans can learn different striking types as a forehand or a backhand, as can be also seen in the image at the right. Furthermore, human motor skills are precise. We can, for example, place the table tennis ball precisely at the desired position on the opponent's table side. Or we can pick up very fine needles. We can also quickly adapt to different task specifications, which means that we can, for example, reach different positions easily. And finally, we can learn new and different skills for the same task. For example, reaching a target from different sides while avoiding an obstacle. Thus, we can easily extend our skills, enabling us to have modular motor skills. The question we ask ourselves is, how can robots learn skills with these properties in order to be flexible and prepared for environmental changes? So let's ask ourselves, would we need to train skill libraries for robots that have the aforementioned properties? First, consider this easy example on the left, where a planar robot needs to reach the red point while avoiding the black obstacle in the middle. There exist different solutions to this task, reaching from the left and from the right to the target. Therefore, our model needs to be able to represent multimodal solutions. Ideally, we expect the model to be able to solve the task for different task specifications. But at the same time, we need to enforce that our learned solutions are precise. This means our model should be an expert in a local region of the context space, which is marked as a sign circle circles in the left image. One context here specifies the target to reach. Given our local experts, our model needs to be able to cover the whole context space and therefore be highly adaptable. Finally, we desire that our model can adjust its model complexity by adding and deleting local experts and therefore be modular. A suitable model which can handle these properties is a mixture of experts model. Commonly, a mixture model is given through the shown equation, where we have a gating distribution pi of O given C, which chooses the component O given a context C. Subsequently, the component pi of zeta given C, O, adjusts the parameters of the movement primitive controller given the context. This component represents one mode of the solution space as can be seen in the right image. We model our components to be a linear conditional Gaussian distribution. However, the model given in this form doesn't enable each component to be an expert in a local context region. Therefore, by applying Bayes' rule, we rewrite the gating as can be seen in the equation. To this end, we model the component-wise context distribution pi of C given O instead of the gating distribution pi of O given C. Since these component-wise context distributions are modeled as Gaussians, the corresponding components only see context samples from a local context region as visualized in the green circle in the image to the right. Since we also optimize these distributions, we allow each component to adjust its curriculum by focusing on the context regions they favor to solve. At the same time, this avoids that a component has to span over the whole context space. Furthermore, we model the weight distribution pi of O as a categorical distribution. Given this hierarchical model, the next question we need to ask ourselves is how are we going to optimize this model, and more precisely, which objective do we need to optimize such that our model has the given properties? We start with the common contextual policy search objective. Optimizing this objective trains the adaptivity component of our desiderata to the model. As can be seen in the objective, we try to maximize the expected return, where the contexts C are sampled from the unknown context distribution P of C of the environment. Next, to enforce versatility in our mixture model, we make use of the maximum entropy objective by adding an entropy bonus to the objective. Still, the objective in the current version will not allow specializing to local context regions, as the contexts come from an unknown context distribution P of C. We therefore make use of the curriculum learning approach as also described before. Now we can see that the contexts are sampled from the model's context distribution pi of c, which is at the same time optimized. To enforce the optimized context distribution pi of c to recover the environment's context distribution p of c, we also penalize deviations between these distributions with the KL terms, scaled with the scaling parameter beta. However, note that this objective will enable the model to only focus on the context regions it can cover. Thus, in context regions which are not covered, the mixture model will perform badly. Unfortunately, this objective is not easy to optimize due to the presence of the mixture model. However, we can apply a decomposition to this objective similar to prior work, such that we are able to optimize each component independently. In this toy example, we visualize the properties of the algorithm. The task for the planar robot is to reach the one-dimensional line to the right, which forms the one-dimensional context space, by avoiding the red obstacles in the middle. Samples of a component are plotted in one color, where the corresponding local component-wise context distribution is plotted to the left in the same color. We can see that the context distribution is updated and all allows that components focus on a local context region. At the same time, components are incrementally added and quickly converge to context regions that are not covered yet. However, overlapping regions in the context space allow having several solutions to the same context regions, as for example can be seen by the blue and purple components, which reach from the right and the left side respectively. We also have conducted experiments on sophisticated simulated robot tasks. In the beer pong task, the robot has to throw a ball into the cup on the table. The different positions on the table form the two-dimensional context space of the task. Different robot joint trajectories lead to different ball trajectories. The video shows examples where we fixed the cup and sampled different solutions to this given context. We can see that the ball flies directly into the cup or bounces once, twice or more on the table before landing in the cup. We compared our method to other methods which are also able to optimize mixture models. The mean rewards show that we are able to achieve more qualitative solutions than prior work while learning versatile skills. A second sophisticated experiment is to let the robot learn to play table tennis. The four-dimensional context space is composed of the ball's target landing position, shown in yellow, and the incoming landing position, shown in red, in the video. The robot learns to strike differently for a fixed context and therefore is able to learn versatile skills. For example, one can observe for some contexts that it is returning the ball with a forehand, which can be described by striking with the green side of the racket, or with a backhand, which can be described by striking with the red side of the racket. We can also see that the robot learns smashing leg strikes, as well as striking to the left and to the right. In this work, we have introduced a model which can represent multimodal solutions, which allows training local experts in order to provide precise solutions, and which allows adapting the model complexity during training. We have presented the underlying objective, which enables the model to learn skills with the aforementioned properties. In future work, we plan to improve sample efficiency by enabling experience sharing between the components, for example by inter-option learning, and we plan to extend the approach to more complex models such as nonlinear mixture of experts.